Right, so weak acids. Weak acids gets covered at GCSE, sort of just, really, only just covered. At the most, it's 2 marks on an exam. Difference between weak and strong acids. Can anyone name me a weak acid off the top of their heads? Go on, Alfie. Any of the carboxylic acids. Okay, that's a really good answer. So the weak acids tends to be the organic acids, as opposed to the mineral acids, you know, the ones that are made from rocks and minerals like hydrochloric, sulfuric, nitric acid. Those are all mineral acids. They're also all strong acids. Any of the organic or carboxylic acids are the weak ones. So I'm going to do most of my examples today with good old ethanoic acid. Say good old because you all enjoy it on a regular basis in what? Vinegar. Yeah, vinegar is about 5% solution of ethanoic acid. So, yeah, we see a lot of that around. What is it that distinguishes the weak acids from the strong acids? What does that word weak mean? What do the words strong mean when we're talking about acids? Can I point this at this desk here?
Is it the ability to dissociate and get a H+?
Okay, perfect. So of a strong acid, we would say
it easily.
Can we go for completely?
Yeah.
Okay. Whereas a weak acid,
not as. What was the word they used?
there is a word, yeah. Rather than not completely, which tells us what it doesn't do. Good word there. Yeah, it's one of those words that we use, which perhaps, okay. Partially. Okay, so weak acids partially dissociate into ions. So if I was to write the equation for the dissociation of ethanoic acid, straight off it's different because I've used a reversible arrow. And then the H plus that comes off is the H plus in the acid group, the COOH group. So we get that kind of reaction there. That ion there, it's the ethanoate ion. I'm going to be referring to ethanoate quite a lot in this topic. Okay. Well, we've already come across equilibrium in this topic, haven't we? We came across it in water's dissociation to make H plus and OH minus. So you remember that if I've got an equilibrium, I can write an expression for the equilibrium constant in terms of concentrations, please. So Kc. Can you write me the expression for Kc for this equilibrium, please? Remember, whenever AQA use the word expression, they always mean a mathematical type thing. A equals B is an expression. If they want you to write an equation, they'll use the word equation, meaning chemical equation. What have you got?
Concentration of CH3CO times concentration of H over concentration of CH3CO.
Okay. Now, because this specifically specifically refers to the dissociation of an acid, we're going to call that special K, Ka. The little a there is just a reminder, really. It doesn't mean anything mathematical. It's just a reminder that we're talking about an acid. If we were talking about a base, it would be called Kb. All right, but it's Ka to remind us that it's talking about an acid. Okay, so let's see if we can make some inroads into this. Let's say about 1% of molecules are dissociating. So if my concentration of ethanoic acid was 1 mole per dm cubed, and about 1% of the acid molecules are dissociating, could you work out a value of Ka for me, please? Put an ear before the front there. It's a bit less than 1% actually. What is it now? What is it? Dissociation. What have we got?
1.01 times 10⁻².
So if you've done this properly, you would have said I've got about 0.01 times 0.01 on the top. 0.99, strictly speaking, would go on the bottom, because if 0.01% of our ethanoic acid is dissociated, then I've only got 0.99 left on the bottom. Of course, it won't make a huge difference, which is about 1 times 10 to the minus 4. In fact, it's a bit less than that. I did just look it up and I've lost it already. What did I just say? 1.76. Ka is 1.76 times 10 to the minus 5. So it's a little bit less than that, which means that in ethanoic acid, there's slightly less than 1% of molecules are actually dissociated into ions at any one point. So when we're thinking about this equilibrium, it's a long way shifted to the back. For every H plus we've got about 100 undissociated ethanoic acid molecules. And it's worth reminding ourselves that an ethanoic acid molecule on its own is not acidic. The only thing that's acidic is H plus. So if you put your hand into a beaker full of undissociated acid molecules, it wouldn't affect you at all. Because there's no acid there, there's only acid there. The only acid that exists is H plus ions. So it's only when ethanoic acid dissociates that it makes an acid. So that means that the concentration of H plus is very much lower than the concentration of the acid. So if our concentration of the acid was 1, the concentration of H plus ions is about 0.01. We'll work that out in a moment. Okay, let's simplify this equation a bit, because at the moment it's a bit unwieldy. But we made a couple of assumptions there. The first assumption is that if one of those ethanoic acid molecules dissociates, it'll make one of those and one of those. So the concentration of those two are roughly the same. Okay. So assumptions we're going to make, and you need to know these, by the way. So the concentration of ethanoate and the concentration of H plus are roughly the same. Under what kind of conditions would they start to become a bit different? No. If we change the temperature, well, this reaction is almost certainly endothermic because we're breaking bonds. At a higher temperature, the equilibrium position would shift in the endothermic direction, which would increase the concentration of both of those, but probably equally. So they'd still be equal. Yeah?
Would it be in alkaline conditions because the OH minus would react with the H?
Oh, okay, yeah. I mean, yeah, if we added other chemicals, obviously, then that would break down. I'm talking about a solution of dilute acid, not with anything else. Under what conditions? We did something similar with HCl and pH. Do you remember? We talked about how the assumption that concentration of H plus is the same as concentration of an acid doesn't always work. Under what conditions? Looking back in the topic booklet might help here. Kieran's looking right at it right now. No, it's not coming up. Do you remember I asked the question, what's the pH of 1 times 10 to the 8 mole per dm cubed HCl? What was the answer?
8 or something.
Well, yeah, it's clearly not 8, is it? Why is it not 8?
Because it's an acid.
Yeah, but a better reason. I mean, it can't be 8 is what you're answering there, but why isn't it 8? What have we missed out in that assumption?
Something like that water can dissociate?
Right, water can dissociate. So under what conditions would I expect the concentration of an ethanoate and H plus to deviate?
Aqueous.
No, I need a bit more. Give me a bit more. Say again?
Low concentration.
Right, low concentration. 10 to the minus 8 moles per dm cubed is a very low concentration. And those kinds of concentrations, the maths isn't going to hold up because water's dissociating as well, and that will produce some H plus ions. But for most everyday concentrations, 10 to the minus 2, 10 to the minus 3, it'll be fine. So I'm just going to say for most laboratory concentrations, if you're talking about, I don't know, the concentration of ethanoic acid in your blood or whatever it is, then things might differ a bit, because often concentrations in living systems are very, very tiny. Okay. All right. We can make another assumption as well. It's going to make our lives a bit easier. Down the bottom here, I said that the concentration of ethanoic acid should be 0.99 because 0.01 of it is dissociated. But 0.99 and 1 are very, very close together in terms of, numeric value. It's going to give us about a 1% error in our calculations, which works out as about the third sig fig. And it'll make the calculations much easier. So we're going to assume that the concentration of ethanoic acid molecules is the same as what's written on the label of the bottle, or what's written in the question in the book. So there'll be a tiny amount of it dissociated, but if we ignore that, it'll only make a tiny error in our calculations. In fact, since less than 1% of acid molecules dissociate, it'll be a less than 1% error. So actually, it'll probably disappear in the third sig fig. Okay, so for a weak acid, the error is probably around about 1%, which we can live with because it makes things so much simpler for us. If I put those assumptions into my equation for Ka, it's starting to look much, much more solvable. Close? Okay. So H plus times itself on the top, concentration of the acid, whatever's written in the question or on the side of the bottle on the bottom. And now if I rearrange that, I can make a handy little formula for me, making H plus the subject. Somebody do that for us? Go on.
The square root of Ka times the concentration of acid.
Thank you very much. Okay. You can quote that as it is. I'm just going to call it the weak acid formula from now on. But bear in mind, it comes with a couple of assumptions attached. It won't work at low concentrations, and it'll only work as long as the acid is a truly weak acid. If the weak acid gets quite strong, and then the accuracy breaks down, and we might have to take into account the fact that the concentration of the acid is different from the concentration of the molecule. But let's just use that as it is for the time being. So let's calculate the concentration of 0.1 mole per dm cubed ethanoic acid, pKa. It's on the top of the board. There it is. Sorry, Ka, not pKa. You don't know what pKa is, do you? No, but you know what Ka is. I'll talk about pKa in a moment. inorganic gases, certainly four. Right, what do we got? Can I answer you? No number? No number? Stick them in there. It's square root. That's H plus. Oh, that's fascinating. What'd you get, Karen? 2.88. So, yeah, so you should have H plus is the square root of 1.76 times 10 to the minus 5 times 0.1, which is, of course, the square root of 1.76 times 10 to the minus 6. I can't remember what that is. Square root of 1.76 times 10 to the minus 6. 3 times 10 to the minus 3. Hit the log button. Change the sign 2.88 given to 2 decimal places. Did you get that?
No, I didn't know you had to do the pH.
I've written concentration, that's why. I can see why that would be confusing. What I should have written is pH. That would have made more sense. That's gone out live on my feed now. What will my followers think? They'll be desperately upset. Yes, I should have put pH on the board. Thank you. That would have, because the concentration obviously is 0.1. Okay. Should we do another one? Okay, I'm just going to make it slightly harder. Okay, if pH is minus log to the base 10 of H plus, what do you think pKa might be?
Minus log of K.
Minus log of Ka. What about POH? What might that be? What do you think, Kieran? Minus log. Concentration of it. What about pKw?
Use OH and then the H plus on the other side level. Oh, minus log, sorry. Minus log.
Minus log of?
The concentration of OH minus and then the H plus level.
Right, well, let's stick with the series, yes? You don't have to tell me what KW is.
Oh, just minus log of KW.
Minus log of KW. Okay, so we have this idea then that putting a little p in front of something is shorthand for minus log of. Remembering, of course, that OH and H plus are ions, but so we've seen that before. Now, the pKa one is useful because if I take pKa data for ethanoic acid, it becomes a much easier number to work with. pKa. So pKa for ethanoic acid is 4.76, which is a lot easier to work with than 1.76 times 10 to the minus 5, which I think you all agree is quite small. just a thought here. We'll just deviate slightly. If I put a chlorine on my ethanoic acid there, the pKa goes down to 2.86. So let's just ask one question first. Does that mean that chloroethanoic acid is a stronger acid or a weaker acid than ethanoic acid? What do we think? Stronger or weaker?
Weaker,
Why?
because I don't know how to explain it, but I just think that it's weaker. Like chlorine would take priority or something.
Well, we'll worry about the why in a moment.
Is it because
Is what because?
that it's weaker?
Because
Because there'll be a larger Ka, so there'll be a higher constant.
larger Ka. Yes, that's got a larger Ka than that. We're all happy with that. Larger Ka means
That it's stronger.
that it's dissociating more, doesn't it? Okay, if it's dissociating more, then we're making more H plus, so it's a stronger acid. Think of it in terms of pH, right? Low pH numbers mean strong acid, don't they? Higher pH numbers mean weaker acid. And pKa works in the same way. So ethanoic acid is a weaker acid than chloroethanoic acid. Can anyone think why that might be? It involves pi. And who doesn't like pi? What's pi? What is pie? Cherry pie? Steak and kidney pie? Why would you eat kidneys? That's disgusting. Let's go back to cherries. Apple and blackcurrant, that's a good pie. Or apple and blackberry, that's a good pie this time of year. Or blackberries are probably gone by now. But I digress. What does pi stand for?
What's over the diameter?
The positive inductive effect. Do you remember that?
Oh,
Yeah. So the chlorine, because the chlorine's electronegative, it's pulling electrons away all the way down the chain, which pulls electrons away from the O minus, which makes the O minus a bit less of an O minus, which makes it a little bit less attractive to the H plus. So therefore the H plus is less likely to team up with the O minus, and therefore the H pluses are more likely to be available to go off and do their acid thing. We'll come back to that when we do carboxylic acids as a proper topic, probably towards Christmas. But I hate to leave something unexplained on the board. Okay, so calculate the pH this time. We'll actually ask the question correctly. Okay, so calculate the pH of 0.1 mole per dm cubed chloroethanoic acid. And there's your pKa. Okay, so it's the same question, but we've added an extra step, and got the question right.
So was there any units for
Hey, sorry, what?
Is there any units for Ka?
Units for Ka. Yes, there would be units for Ka because it's concentration squared over concentration. So it would just be units of concentration. But once we've logged something, the units become meaningless. So anything with a log in it doesn't have units. pH doesn't have any units. It's just a number. So we're going to have tables of pKa. I'll leave that there. These data books are great because they're old. People have often written things. Andrew Prescott, 5C. There's Andrew Prescott, probably about my age now. What page are you on there? Oh yeah, I like that one because of the.
Look at that. It's too low.
I'm sure there's stuff online as well, but we like books.
Yeah, no, I heard no, so I don't know if it's my theory, just being dysfunctional.
Oh, we're gonna stop on minus level.
Don't worry, you're feeling left out. Can you see that? No, no. Some pKa data for us all. Yes, there we go. That's very exciting. Okay. Right. So yeah, there we go. Lots of pKa data there. For us to look at. Okay, so I asked you to complete exercise 1, I think, a while ago. I'm just going to tack exercise 2 onto that now. You've got 10 minutes to crack on with that now. And I'll put that all on Satchel as usual.